All right, kids, so we're back. I'm in the class with my mask on, and we're going to do section 1.3, practice question 4. So let's see what it says. It says, to get to the cafeteria entrance, a teacher walks 34 meters north in one hallway, then 46 meters west in another. The entire motion takes 1.5 minutes. Determine the teacher's resultant displacement, average speed, and average velocity. So the first thing you have to do is you have to establish a direction. So this is what you do to establish a direction. I say up the page is north. That's the first thing you do. And then you draw a diagram. Now the first displacement is right there, and it's 34 meters north. Then they go 46 meters west. Okay, now, why did I put the vectors like this? Because I taught you in the video something called vector tip to tail addition, where you draw the first vector, and at its tip, you put the tail of the second vector, and you add them up. That's what I taught you. So since it started here and it finished there, this is what the addition looks like. All right, this is what the addition looks like. And what you're adding here is going to give you the displacement. Why? Because the teacher started there. There's the teacher's initial position. Then the teacher ended here. There's the teacher's final position. So we connect the initial position, that's an I, to the final position, and it's telling us that are studying this motion, look, the teacher is now so many meters away in a particular direction. So that's why we connected the initial position to the final position, because I can say, look, the new position is so many meters away in a particular direction. That's what we can do. That's why this yellow and green arrow becomes a representation of the displacement. So let's talk about displacement. Displacement is a vector. Oops, let me write that out again. Displacement is a vector. Vectors have two parts. They have the magnitude part and they have the direction. Oops, don't want to do that. They have the direction part. The magnitude part is shown by this right here. Magnitude of the displacement vector. Well, look where it is. It's part of a right angle triangle. So in order to find that magnitude, all we do is use, remember these straight lines up and down are magnitude, they're not brackets. I talked about that in the video. All we have to do is find the magnitude by using Pythagoras. So it would be, look, the magnitude of 34 meters north squared plus, what's the number there, 46? The magnitude of 46 meters west squared. All right, so since it's telling us, look, I'm only interested in the magnitude. I'm only interested in the magnitude. I totally ignore the north and the west. I'm not interested in it. It's only magnitude I'm interested in it. So we do Pythagorean theorem. 34 squared plus 46 squared. We press equal on our calculator. Then we square root that. And we get 57.2. So what have we found out? We found out that the final position is 57.2 meters away from the initial position. But it doesn't tell me which way to point. This is a vector. I need to know in what direction is it 57.2 meters away. So that's where I got to use an angle. Now listen, you always draw the angle down here near the initial position, always. And then we use something you've learned in math class, trigonometric functions, right? Have you not learned sine, cosine, and tangent? I hope so. So it's tan inverse. I hope you kids have learned the inverse functions. Have you learned the inverse functions of these? Okay. So look, tan inverse is opposite 46 meters. Whoopsie. 46 meters. Let me clean that up. I have no idea what happened. There we go. Divided by adjacent. Adjacent literally means next to. 34 meters. So I get my handy dandy fancy dancy calculator and I use the inverse tan function of 46 divided by 34 and I get 53.5 degrees. Okay? Now I can combine these two things and come up with the complete vector and say the displacement is 57.2 meters, 53.5 degrees. Now I got to think about this. Here's the angle theta. I know that this is north. Straight up and down here is north, but it's been shifted to the west by a certain amount. It's been shifted towards the west by 53.5 degrees. So I say 53.5 degrees west of north. And now I have my displacement. And it's literally telling me, look, you are now 57.2 meters away from where you started in a direction of 53.5 degrees west of north from where you started. That's what it's telling you. Now, does that mean that the object, the teacher, actually moved in a direction that was 53.5 degrees? No. It's like an averaging out. The teacher went north, and then the teacher went west. All it's doing is telling you a comparison between where you started and where you ended up. It doesn't tell you how you got there. Only this is where you started, this is where you ended up, this is initial position, this is final position, and I'm comparing the two. That's it. Don't read too much into this. Now, some kids are saying, well, look, sir, the textbook's giving me an answer of 36 degrees north of west. Well, first of all, let's maybe round this off to 54 degrees, okay? Just for simplicity's sake. And let's draw this. There's north, there's west. And it's telling us it's 54 degrees north of west of north. Okay. So there's the 54 degrees right there. But the textbook is using this angle down here, which is 36 degrees. In math class, we would have learned these to be complementary angles. Do you remember that from math class? Complementary. Complementary. Complementary with an E, not complementary with an I. Complementary with an I says, oh, you look very nice today. Complementary with an E is telling us I'm completing the 90 degrees. Okay? So instead of writing it as 54 degrees west of north, they write it as 36 degrees north of west. Guess what? Same thing. It means the same thing. So that's the first part. Now they want us to find the average speed. So let's get a new page up here. The average speed. Well, speed average is a scalar. It's not a vector. So all I need is 34 plus 34 plus 46 is 80, right? So there's your 80 meters. And it took 1.5 minutes, which is 90 seconds, right? 1.5 minutes is 90 seconds. And we get 0.89 meters per second. Notice this is a scalar. There's no direction to be had whatsoever. The next question is, what's the average velocity? Okay, well now we're into a vector. So now I have to put in 57 meters. It doesn't matter which angle you use. A 36. You want to use a 36, that's fine. 36 degrees north of west. And then we divide it by the 90 seconds. 1.5 minutes is 90 seconds. So it's 57 divided by 90. And we get basically 6.63. So that's 0.63. That's a horrible 6 there. Meters per second, because I got to put the unit in, meter per second. And then I put the direction in, same direction, 36 degrees north of west. Now remember, this is an averaging of the motion. Did the person actually move in that direction? No. It's just a mathematical averaging. Okay? Is that okay, buddy? Okay, that's the way we do that. I'm going to post this.